I'm Scott Hall, and I did my project this summer on rift propagation in the Fimbul and Ross ice shelves in Antarctica with Dr. Jeremy Bassis, who unfortunately couldn't be here today. He's been out of town all week. But my project fell under a type of science called glaciology, which falls into the oceanic part of the atmospheric, oceanic, and space science department here. So an important question to kind of lead off with would be, what is glaciology and why should you care? So glaciology is not just the study of glaciers, but the study of ice. And as thrilling as that probably sounds, the reason why the study of ice is important is because the ice on our planet is important. The ice on our planet in the polar caps holds about 70% of the fresh water on the planet. And just to put that into scale, if all of the ice in the polar caps were to melt, there would be a 60-meter rise in sea level. Now, that's not anything anybody thinks is going to happen anytime soon, but that puts into scale how much ice really is on the planet. It also reflects sunlight, which helps control the climate, and various other things. The question in glaciology today is, how is the ice affected by climate change? 10 years ago, it was, is there climate change, and can we tell by looking at the ice? Now it's, yes, there is climate change. What is it doing to the ice? This is Antarctica. This is basically if you took a globe and looked up at the bottom of it. This is a map projection of it. If you look at this, you'll notice that there is a black line, and then there's the edge of the white. So Antarctica is a continent. There is land, and the black line on this map is the edge of the land. But you'll notice that in a lot of places, a couple big places, and then around the edge, a lot of places, the white continues off past the black. And so in those spots, that's where the ice continues to flow out into the water but stays as one cohesive shelf. My work focused on what the ice is doing at the edge of the shelves. So it's important then to understand how ice shelves work to kind of understand what I was looking at. So as I said, the ice shelf is not grounded. It's freely floating ice. So in this illustration, from this point over, it's an ice shelf. You can see that it's part of the ice sheet. It just keeps going, but it leaves the land at the grounding line and then continues out. The ice is constantly flowing due to gravity. So if you think about when you spill a cup of water, the water spreads out on the table, keeps going, thins out. The ice in Antarctica is doing that just really, really slowly. So it is a fluid, but it's a very slowly moving fluid. But it's doing that, so it's continually spreading out. And the ice gets out past a point where it's in equilibrium, and rifts or cracks start to form, icebergs break off. So the ice gets out to about here, and it's too far out, it gets unstable, it breaks off a chunk. And then it's a little bit shorter, but the ice keeps flowing, it gets out here again, breaks off another iceberg. This is natural, this is normal, but the important part that glaciologists are looking at is the rate. How fast is the ice moving? How fast are icebergs breaking off? Is that changing? What is climate change doing to that? Just to kind of better illustrate that, this is an ice sheet. If you look at it, this is a satellite images, so this is like looking down at one. And if you look at this, so we've got the ocean up here, the edge of the ice, and then it's kind of hard to see necessarily, but I know that this is the grounding line on that. So this is the edge of the coast, and then the ice continues to flow out. And this is the ice stream that's feeding this ice sheet. So this is where the ice is moving a bit faster than everywhere else, like a real stream kind of feeding a lake. So the ice is moving faster, and it moves, and then the ice continues to spread out. So, and then as it flows out, it gets out to here, and then this edge is where all the iceberg excitement is happening with the cracks, the rifts, breakage, and that kind of thing. So the first half of my project, I looked at images of ice shelves and looked at rift propagation, looked at how fast the rifts are growing. The images that I used were taken by MODIS, which is the Moderate Resolution Imaging Spectroradiometer, which is on the NASA Terra satellite. The images go back about 10 years. It's been the past decade that the images that we had were good for. So again, here's Antarctica. The two shelves that I was looking at are the Ross down here at the bottom and the Fimbul way up at the top. This is a portion of the Ross ice shelf. if you look, there really doesn't look like there's a whole lot going on at first glance. You've got the black is the ocean, the white is the ice, there's some clouds, there's a little bit of sea ice up there at the top, but there's really not a whole lot of very interesting stuff going on. But if you zoom in on this part, and you blow it up, you can see that there actually is a rift through the ice. And for scale, this is about 50 kilometers from there to there. This rift was one that I found. So I started off by looking at the database at the National Stone Ice Data Center of all the different images. They have images for all the different shelves, and it took a while for me to find some interesting rifts, and this happened to be one. So I took all the images that they had for this rift, pulled them into Photoshop, used the ruler tool, and measured in pixels how long these were, because we knew that one pixel was 250 meters, so we could figure out exactly how long they were, how it changed over time. Averaging it out for this particular rift, these are the lengths that we got, the yearly averages. So you can look at this and see that it started off at about 45 kilometers. Over a period of about 7 years, grew pretty steadily to about 47.5 kilometers, and then at the end it looked like the past 2 years it stopped. And the question we were left with was, well, why? But before I do that, I have a movie that I put together of all the images of this shelf, so you can kind of visually see what was going on with this. So when I play this, you'll notice a lot, but I want you to notice two things. One, if you keep your eye on the rift tip, you'll actually begin to see it move out. And secondly, as you keep your eye on that, you'll notice that the whole sheet is advecting out, which is pretty cool. We were talking about how the ice is flowing, but in this movie, because this square is the same square on the planet, you can watch the sheet actually move its way out. So you can see that there's a lot going on, a lot of clouds, a lot of stuff moving. It was kind of hard to fight through some of the noise with the images, but the second one that I looked at was the Fimbul, which is the opposite side of Antarctica. And this is the whole shelf. You can see that there's a little bit more going on, more ice, but again, you kind of have to zoom in to be able to see really what we were looking at. And this particular part happens to have 4 separate rifts that we were looking at. So we kind of named it just to keep track of them. We had the top 2 parts of this fork, and then this one down here at the bottom. These are a little bit shorter than the ones on the Ross. The top is about 20 kilometers. So they're shorter, but they're still very wide, long cracks in the ice. You'll notice in this image too that this bottom one you can barely see, and we weren't even going to keep track of it, but you'll see in the movie that it had very explosive growth later on in its life, and so when we saw the last couple images, we were like, wait a minute, we got to kind of keep track of this one. So again, graphed out, here are the lengths of those 4 rifts over time. And you'll notice here at the end, you'll see that explosive growth that I was talking about. It's about 10 kilometers of growth in a period of about a month. And when we're talking that usual rates are about a meter a day, growing 10 kilometers in a month is a lot. So that was a very explosive thing. And you'll notice too that while this was doing this, these 3 didn't show any change. And that's important to note too, because this big system, they're all going to be interacting with each other. And so then the question is, so why was that one doing that when the other 3 didn't do anything? And if you look back here, you'll also see that the other 3 rifts each experienced about 2 kilometers of growth in the same period. It was March 2004. They all experienced the same growth. And this bottom one didn't do anything. And so again, the question is, well, why? And you can see that 2 kilometers isn't nearly as much as 10, but that's still a lot of growth, and it's an anomaly compared to the usual rate. So again, I have a movie I put together of the images. You'll see that on the Fimbul there's even more going on. There's a lot of sea ice, there's a lot of change as the seasons move, but if you keep your eye on the rift tips, you can see them as they grow. And you also, if you keep your eye down here on the last 2 images, you'll see this one not do anything and all of a sudden jut out. So